Welcome everybody. So in our last lecture we have seen one type of process scheduling algorithm which was FCFS. This FCFS scheduling algorithm stands for first come first serve type of scheduling algorithm. This FCFS scheduling algorithm was very easy to understand as it was non-preemptive in nature. Non-preemptive in nature means once one process is getting the CPU, it will start running inside the CPU and it will only come outside the CPU once it has completed all its job. So when one process is coming out of the CPU, then only the next process is getting the chance to get inside the CPU. This FCFS scheduling algorithm was implemented using the FIFO queue, first in first out type of queue, and the average waiting time for all the processes implemented by this FCFS scheduling algorithm was very high, because all the processes has to wait for the process which is running inside the CPU to complete its task. Today we will start our discussion with a new scheduling algorithm which is shortest job first algorithm or SJF. Now this algorithm is associated with each process and the length of the process's next CPU burst time. That means here we are not considering whether the process is coming first inside the queue or next in the queue, but we are considering the burst time of the process. Now what is burst time? The time a process is spending inside the CPU for doing the computation type of task. So instead of their order of arrival, here we are considering their burst length. If there is a tie, it is also possible that two processes are having the same burst length. That means say one process is P1 and another process is P2. Both the processes are taking 5 millisecond time period to complete their task. So what happens then? Maybe P1 is coming first, maybe P2 is coming first, doesn't matter. If both of them are having the same CPU burst time, then there is a tie only, because we have to decide which process, operating system is deciding which process to be executed inside the CPU first. So the process which is coming first with the same burst length will be allowed to run inside the CPU first. So here we are considering the FCFS, that means first come first serve type of scheduling in case of same CPU burst length SJF. Now in other words, we can say that this algorithm is regarded as the shortest next CPU burst algorithm. Let us see how it works. This SJF or shortest job first scheduling algorithm is optimal in nature. That means it gives the minimum average waiting time for a given set of processes. We have seen that in case of FCFS, first come first serve scheduling algorithm, the average waiting time was very high, because it may be possible that a long process has arrived first, so it is getting the CPU first and it is spending its long burst time period inside the CPU to do its computation type of task. Maybe the process is having very minimum, small time burst time period, is waiting inside the ready queue for the completion of the task of that long previous process. But in case of SJF, it doesn't happen. Always the process which is having shortest burst time will be executed first. Let us have one example. Here I have given 4 processes, P1, P2, P3 and P4, and their burst time is also written beside. Process P1 is having the burst time 6, though I have not written the unit, but you can consider the burst time is in millisecond. So process P1 is having the burst time 6 millisecond, process P2 is having the burst time 8 millisecond, process P3 is having the burst time 7 millisecond and lastly process P4 is having the burst time 3 millisecond. Now, if we consider the FCFS scheduling algorithm, you can compute that the average waiting time is 10.25 millisecond time period for each and every process. But if we consider the shortest job first scheduling algorithm, the average waiting time will be just 7 millisecond time period, which is much less than the FCFS scheduling algorithm. Now, in my last lecture, I have shown you how we are computing the average waiting time for first come first serve type of scheduling algorithm. The same methodology we are adopting here for finding the average waiting time of SJF scheduling algorithm. Now, though here I have not written the details of how we are computing the average waiting time, I have only written 10.25 millisecond for FCFS and 7 millisecond for SJF, just to make one comparison that SJF is taking lesser time period. Now, I am showing you how we are computing the average waiting time for SJF. Before going to that process, I must consider two issues, that SJF can be of two types. One is the non-preemptive scheme and second one is the preemptive scheme. In case of non-preemptive scheme, once the CPU is given to the process, it cannot be preempted until completes its CPU burst. That is non-preemptive nature of any scheduling algorithm. Once the process is getting the CPU, it will come out of the CPU only after it finishes its task. But what happens in preemptive type of scheduling algorithm? If a new process arrives with CPU burst length less than the remaining time of the currently running process, then that currently running process is preempted. This scheme is also known as the shortest remaining time first algorithm or SRTF scheduling algorithm. So, let us start our methodology for finding average waiting time with non-preemptive SJF. So, here I have again considered 4 processes P1, P2, P3, P4 with their burst times 7 millisecond, 4 millisecond, 1 millisecond and 4 millisecond time period. You look here, with the processes and burst time, I have considered another parameter, which is the arrival time. See here, the arrival time for process P1 is 0.0 millisecond. That means from the very beginning process P1 is there in the ready queue. Process P2's arrival time is 2 millisecond. So, process P2 is arriving after 2 millisecond time period. Similarly, process P3 is arriving after 4 millisecond and process P4 is arriving after 5 millisecond time period. So, let us draw the Gantt chart for this non-preemptive SJF. So, first at the 0.0 millisecond time period, as only process P1 is there, no other processes are there in your ready queue. So, we have to work with only process P1 and process P1 starts its execution at 0 millisecond time period. Now, here we are considering non-preemptiveness of the scheduling algorithm. What non-preemptiveness says? That once a process is getting the chance to get inside the CPU, it will only come out once it is completing its execution totally. So, as P1's burst time is 7 millisecond, it will only come out of the CPU after 7 millisecond time period, completing all its tasks. So, starting at 0 millisecond time period, it will be completed after 7 millisecond. That is why in the Gantt chart from 0 millisecond to 7 millisecond, I am having process P1. Now, when process P1 is completed at 7 millisecond time period. So, by 7 millisecond time period, all 3 processes P2, P3, P4 they have arrived in my ready queue. P2 arrived after 2 millisecond, P3 arrived after 4 millisecond and P4 arrived at 5 millisecond time period, but already 7 millisecond time period had elapsed. So now I have to consider out of P2, P3 and P4 that process which is having the lowest burst time. So see here, process P3 is having 1 millisecond burst time and process P2 and P4 are having, both of them are having 4 millisecond burst time period. So we have to start with process P3. So at 7 millisecond time period, process P3 starts its execution and its burst time is only 1 millisecond. So it will work inside the CPU for only 1 millisecond and from 7 millisecond till 1 millisecond. So at 8 millisecond time period, P3 is completed. So after 8 millisecond time period, you see at the Gantt chart, process P1 gets completed, process P3 also completed. Now we are having two processes in our hand, process P2 and process P4. Look here, both of them are having the same burst time period, that is 4 millisecond. So with which process to start? I have told you that if there is a tie, then I have to follow the FCFS, first come first serve type of scheduling algorithm. So out of P2 and P4, P2 arrived at 2 millisecond time period and P4 arrived at 5 millisecond time period. That means P2 comes first. After the completion of P3, now I have to start with process P2. So P2 will start at 8 millisecond time period and will work inside the CPU for 4 millisecond time period. So it will be completed and come out of the CPU at 12 millisecond time period. Now P1, P3, P2, 3 processes are completed. I am having just a single process in the ready queue, that is process P4 with the burst time 4 millisecond. So at 12 millisecond time period, P4 will start its execution inside the CPU and will be completed after 4 millisecond. That means at 16 millisecond time period, P4 is also completed. That means starting from 0 millisecond time period, all these 4 processes are taking total 16 millisecond time period for completion of their work. You look at the burst time, 7 plus 4 plus 1 plus 4 equals to 16. So all the processes are completed by 16 millisecond time period. That is the Gantt chart. Now next thing is that we have to find the average waiting time. So for process P1, what is the waiting time? Process P1 arrived at 0 millisecond time period and it starts its execution at 0 millisecond time period. So it is not waiting for anybody. That means its waiting time is 0. That is written here. For process P1, the waiting time is 0. For process P2, look at the Gantt chart when P2 starts its execution at 8 millisecond time period. But the thing is that it has arrived inside the ready queue after 2 millisecond time period. So the waiting time for P2 is 8 minus 2 equals to 6. That thing is written there, 0 plus 6. Next is process P3. So P3 in the Gantt chart is starting at 7 millisecond time period, but it arrived inside the ready queue at 4 millisecond time period. Its arrival time is 4 millisecond. So how much time it is waiting inside the ready queue? P3, for P3, 7 minus 4 equals to 3. So the waiting time for P3 is 3. And lastly P4. P4 starts its execution at 12 millisecond time period in the Gantt chart. But you see what is the arrival time for P4? That is 5 millisecond. So 12 minus 5 equals to 7 is the waiting time for P4. So finally, to find out what is the average waiting time for all the processes, we are adding 0 plus 6 plus 3 plus 7 and then we are dividing it by 4 as 4 number of processes are there and we are getting 4 millisecond. So, the average waiting time for all these 4 processes using SJF with non-preemptive nature is 4 millisecond. Next, I shall consider the same thing, but the strategy is preemptive. That means the process can be interrupted by a newly arrived process, and that newly arrived process is having lower burst time period. So, let us see how it works. Same example is given with 4 processes P1, P2, P3, P4. Their burst times 7, 4, 1 and 4 millisecond and their corresponding arrival time is also given. Look at the Gantt chart, it is a little bit different from the previous one. So, at 0 millisecond time period, we are only having process P1 in the ready queue. So, we have to start with process P1. So, P1 is starting. It will work inside the CPU till 2 millisecond time period, because at 2 millisecond time period you see the arrival time of process P2 is 2 millisecond. So, P2 has already arrived. P1's burst time is 7, it has already worked for 2 millisecond. So, remaining burst time is 5 at 2 millisecond time period and P2's burst time is 4. So, which is having the lesser burst time? Obviously P2. So, P1 is preempted and P2 starts working inside the CPU. So, at 2 millisecond time period, P2 will start its execution. It will again work inside the CPU till 4 millisecond time period, because at 4 millisecond time period, you see at the example P3's arrival time is 4 millisecond. So, P3 arrived with just 1 millisecond burst time. So, remaining burst time for process P1 is 5, remaining burst time for process P2 is 2, 4 minus 2, 2 and burst time for P3 is 1. So, out of these 3 processes, P1 is having minimum burst time. So, we have to allow P3 to get inside the CPU. P2 will come out, it is preempted and P3 is entering inside the CPU. And it will work till 1 millisecond time period as its burst time is just 1 millisecond. So, at 5 millisecond time period, P3 is over. It completes all its execution. So, at 5 millisecond time period, I am having 2 processes in my hand. One is P1 with remaining burst time 5 millisecond and P2 with remaining burst time 2 millisecond. But you see at 5 millisecond time period, P4 arrived with 4 millisecond burst time. So, I can say at 5 millisecond time period, I am having number 1 process P1 with remaining burst time 5 millisecond, process P2 with remaining burst time 2 millisecond, P3 is already completed and P4 with burst time 4 millisecond time period. Out of these 3, process P2 is having minimum burst time. So, now I have to work with process P2 after the completion of P3 and P2 will work for 2 millisecond. So, 5 plus 2, 7 millisecond. At 7 millisecond time period, P2 over at 7 millisecond. Now, I am having these 2 processes in my hand, process P1 and process P4 with 5 millisecond and 4 millisecond. Out of these 2, P4 is having 4 millisecond burst time, which is lesser than P1. So, next at 7 millisecond time period, I have to allow process P4 to run inside the CPU and it will work inside the CPU till 4 millisecond. So, at 11 millisecond time period, P4 is over. only now I am having P1 in my hand in the ready queue with 5 millisecond time period. So I have to allow P1 to run next inside the CPU. So it will start working at 11 millisecond time period and will be completed after 5 millisecond, that is at 16 millisecond time period. Again, all these 4 processes are taking total 16 millisecond time period to be completed. And see, the total burst time is again 16, 7 plus 4 plus 1 plus 4. Now I have to find the average waiting time. The average waiting time for process P1. Look at the Gantt chart. Lastly, P1 starts at 11 millisecond time period. But it has already worked inside the Gantt chart at the very beginning for 2 milliseconds. So I have to deduct 2 from 11 and when it arrived at 0 millisecond time period. So I have to deduct the arrival time. So my waiting time of P1 is 11 minus 2 minus 0, that is equal to 9 millisecond. When it last started, how much it worked in the previous, and when it arrives. Next, the waiting time of P2. Look at the Gantt chart. When P2 last started at 5 millisecond time period. But P2 has worked again 2 millisecond time period previously. So I have to deduct 2 here. Now I have to consider when P2 arrived. P2 arrived at 2 millisecond time period. So I have to deduct 2 from here. So 5 minus 2 equals to 3 minus this 2 equals to 1 millisecond. So waiting time for P2 is 1 millisecond. Next for P3, waiting time of P3. Look at the Gantt chart. When P3 started at 4 millisecond time period. Actually it gets the chance only once, and whenever it is getting the chance, it completes all its execution there inside the CPU at 4 millisecond time period. And the reason is that P3 also arrives at the ready queue at 4 millisecond for having the waiting time 0. So started at 4 millisecond, arrived at 4 millisecond. I am getting 0 millisecond time period as the waiting time for process P3. Lastly, the waiting time of process P4. So P4 started lastly at 7 millisecond time period. So 7, and it arrived at 5 millisecond. See at the Gantt chart, it has not worked previously. So it started at 7 millisecond time period, arrived at 5. So I have to deduct 7 minus 5, that is 2 millisecond. The thing is written 9102 there. So to find out the average waiting time, I have to sum up 9 plus 1 plus 0 plus 2, and then I have to divide it by the number of processes, that is 4, and I am getting the average waiting time 3 millisecond, which is lesser than the previous case. So again I am showing you that for non-preemptive type of SJF scheduling algorithm, whatever average time we are getting lesser average time for preemptive type of SJF scheduling algorithm. So this is the case for non-preemptive SJF, where we are having the average waiting time 4 milliseconds, and this is the case for preemptive SJF, where we are having lesser average waiting time, which is 3 millisecond time period. Now there are some problems associated with SJF, that is starvation. Starvation says that in some scenarios a job may wait forever. Say one process is having very long burst time period, so definitely it will be allowed later to get inside the CPU. The smaller processes will get the chance to execute inside the CPU first, So it may happen that the longer process will starve. That is one issue associated with SJF. And so this is one issue associated with SJF. And we can definitely address this issue with some solution strategies, which is aging, which I shall discuss later on. Thank you.